Welcome to the atom graph tutorial. In this tutorial, we're going to learn step by step how to build a basic atom that takes an input image and uses a noise function to perform a per pixel hue adjustment. Now, don't worry, I get it, it sounds complicated, but you'll see it's super easy and it's really barely an inconvenience. So, what's an atom? Well, in the InstaMAT world, an atom is the fundamental image processing node that you can use as a building block when designing your materials or image processing pipelines. Typically, in an element graph, you would use many atoms strung together to create a beautiful material. The visual programming language of InstaMAT's atom graph enables you to develop a seemingly endless variety of different image processing nodes. But InstaMAT's visual programming language is more than just a series of expressions strung together, as commonly found in other shading graphs or tools. The atom graph has a so-called control flow graph that determines how your atom is executed. And why do we need it? Well, with a control flow graph, we can branch or loop in our atom in the same way that is possible in traditional programming languages like C or C++. This allows you to build interesting nodes such as edge detection or even complex ray tracing or rendering features. For instance, InstaMAT's mesh render node, which performs PBR rendering in the element graph, has been implemented using the atom graph. So without further ado, let's get to it. Okay, so we're in InstaMAT, and I'd like to start off with an image I'd like to test my atom graph on. So I've put together a quick element here using a couple instances of the built-in InstaMAT icon node and a tile scatter. I've then composited another InstaMAT icon on top of my scatter by plugging that result into the background of another InstaMAT icon node. So what I can do is I can right-click and choose View Image Output here to view this in the image viewer. And you can see we have a very colorful, funky InstaMAT icon picture. So what I can do now is I can use the Save Image button here in the image viewer to save this as an image file. So I'm going to click and do that. And now I'm just going to drag that image from my Explorer into the Package Management panel here to import it into my project. And so you can see we have this new assets drop down here. I'm just going to go to images, and we've got our funky InstaMAT image.png. By the way, if you'd like to access the package management panel, you can press the 2 key to toggle it on or off, or you can use the 1, 2, and 3 keys to change what's in the left panel. So now that I have an image to work with, let's create a new atom graph by pressing the plus button in the toolbar. And then I'm going to go down to atom graph here. Once an atom graph is created, it's automatically populated by 2 nodes, the entry node and the return node. The entry node is where the execution of the graph will begin. It needs to terminate in the return node. In other words, all atom graphs need to start at the entry and then flow through every node until it finally reaches completion at the return node. So in thinking about the functionality of what we'd like our atom to do, we have to supply it with an image input. So let's create one now. This image input is the image that we'd like to change and process in our atom. So I'm going to go over to the Graph Object Editor here on the right and go to Inputs, and then I'm going to click on the plus button here where it says Add Input Parameter. After clicking on that, I'm going to choose Atom Input Image as the type. I'm going to rename this input by double-clicking where it says Parameter, and I'm going to type in Image. The color we choose with this spectrum is what will be the default color when the atom is initially created. We don't want to use a color, so we'll choose a default image. InstaMAT interprets solid colors and images as the same type of input. This means that you can use an image anywhere a node accepts color information and vice versa. So what I'm going to do here is I'm going to go over to where the pencil icon is, click on that, and then I'm going to go over to this package icon here to see everything that's in my current package. And then I'm going to double click on our funky InstaMAT icon. Now by default, that selected image is going to be what's populating our image input. Next up, I'm going to drag our new input into the canvas. What I'd like to do is tell the atom graph to go through the image provided in our image input and read its information pixel by pixel. So to do that, we can bring in a read pixel node using quick search. So I'm going to click and drag from the output of our image, let go to bring up quick search, and type in read to get read pixel and hit enter. Notice that we also get something else that comes in with our read pixel node, this get texel coordinate. This is what's known as a spawn attachment. A spawn attachment is a node that comes in along with the initial node you're looking for. Get texel coordinate is what you'll most likely put into the coordinate input of the read pixel node, so this is done to save you time. What we can do though is we can right-click our read pixel node and choose Convert Spawn Attachments to Graphs to make these fully fledged nodes. So right now we're reading our image input pixel by pixel, but notice that our entry node has a red warning symbol in the corner. This is because our atom does not flow from beginning to end or entry to return, like it should. This is called an unterminated connection error. So let's hook it up so that the atom graph terminates correctly. So I'm going to take the control flow pin from my entry node, plug it into the read pixel node, and then take the output control flow pin here and connect it to the return node. This way, now our new node is part of the control flow. So the graph is terminating correctly now, but it's not actually doing anything. We're reading the pixel information, but not doing anything with it. Let's write out the pixel information to see if our atom graph is working. I'm going to drag a connection out of the read pixel's result output and let go to bring up quick search, and then I'm going to type in right to get the right pixel node and hit enter. Notice now that we're getting some errors here from the read and write pixel, and that's because we don't have our control flow connecting all of our nodes together to the end. So what I'll do is I will connect the read pixel control flow pin and put it into the input here, and then connect the output of a write pixel to return, and you can see that we're no longer getting those warnings. Now what we need to do is give this information to the output of our atom graph. We can do that by clicking on our graph and dragging in the output automatically assigned to our atom graph into the canvas. Make sure when you click on the canvas that you're viewing the graph object editor, which you can find by pressing Shift-1. Let's take the result of our write pixel node and plug it into the value input of our output. Again, we have to remember to connect the control flow pins, so what I'll do is I will connect the write pixels control flow pin to set output, and then the output control flow pin into the return. So now that we have an input and output of our atom, let's test it out. But before we can do that, let's apply a name, category, and description for it. So clicking on the graph again, we see we have this metadata in our graph object editor. I'm going to change the name to noise-based hue. The category is going to be image adjustments. And for the description, I'm going to write performs a noise-based hue adjustment on the input image. Now you can save the graph by going to File, Save Graph. You can also save the entire package. And I'm going to create a new element to test out our atom. So again, I'm going to go to the plus button on the toolbar and click on Element Graph. Now I'm going to drag the noise-based hue atom that we created in our package into the canvas of our element. Now you can see that our noise-based hue is using that default image that we set. Let's also try supplying something different into the image input. For instance, I can use a text node. So I'm going to right-click to bring up quick search, type in text. I can double-click it here to bring it in. And maybe what I'll do is I'll scroll down here and perhaps bring up the font size just so we can see it a bit better. And now I can drag this output into the input of our noise-based hue, and you can see it's now accepting that image information. If I'd like it to go back to the default image, I can click on this connection and hit delete. So we've created an atom graph, read in some pixel data from its input, and immediately outputted the results. Let's see what we can do with that information. So I'm going to go back to my noise-based hue atom. And what I'd like to do is I'd like to make some space between my read pixel and my write pixel nodes. InstaMAT allows us to do this by positioning my mouse between the two nodes, holding the control key, and pressing the left and right arrow keys. As I mentioned before, we want to create an atom that adjusts the hue of our input image. So let's bring in an HSL color adjustment node. Now, here's another way to use quick search to bring in a node in between two other nodes. If I right-click the purple connection here for the result of the read pixel, I can right-click to bring up quick search, and I'm going to type in HSL. This locates the HSL color adjustment node, so I can hit enter. You can see that the result is automatically plugged into the color input of our HSL adjustment, and you can see that it's trying to connect some of the control flow and outputs as well. So now what I can do is I can connect the read pixel control flow pin to the input control flow pin of the color adjustment node. Now let's take a look at what this node is doing. If I go over to the hue here, I can change the value by typing in a number, or I can click and drag these two triangles to increase the number. To see what I'm doing though, I'm going to pan over and right click on the output here and choose View Image Output. Now we can see what's going on. I can go back to the HSL color adjustment and click and drag to see that we're rotating and transforming the color hue. Now, if I typed in something like 1, you can see that we're doing a 360-degree transformation here and nothing changes. So it's better to type in something like 0.5 to do a 180-degree rotation. Now, this is great, but let's make it more interesting by using a noise function to randomize our hue shift. In the canvas, I'm going to right-click to bring up Quick Search, and I'm going to type in Perlin noise. You can see we have this Perlin noise 2D option. I'm going to double-click that to bring that in. And now I'm going to connect the result output to the hue input of the HSL color adjustment node. You can see that the Perlin noise is connected to the hue, but it's not exactly doing what we want it to. Right now, it's transforming all of our pixels at once. We don't want that. Instead, we'd like to adjust the hue 1 pixel at a time. This is a great use case for that get texel coordinate spawn attachment that we got from the read pixel node. So I'm going to connect the coordinate output from the get texel coordinate and plug it into the position of our Perlin noise 2D. I'm then going to click on the Perlin noise 2D and change the scale manually to something like 6 for the X and 6 for the Y. You can now see that we're getting a more interesting effect here. I'm then going to save my graph and go back to the element that we created earlier with the text. Now, if I click on the noise-based hue, I can change the seed, and you can see that we're getting some updated results. Another way of viewing the output of a node in the image viewer is just by left-clicking on the output itself. That's automatically going to populate it into the 2D image viewer. And so now we can see, as I adjust the seed, not just the canvas preview, but also the image viewer is going to reflect my changes. What's more is now I can connect the text output to our noise-based hue again. And what's interesting though is that you can see nothing's happening. And that's because we need to add some saturation to our text. So I'm going to click on the text and I'm going to change the font color here. And I'm going to click on the little palette icon here and just drag this saturation up. Now you can see that our text is being adjusted, but also our alpha channel is being respected. So we're randomizing our hue based on the Perlin noise we added in our atom graph, but let's add a little more functionality to our node to give the user more parameters to tweak and customize. So we're back in our atom graph, and what I'd like to do is give the user the ability to change the scale of our noise. To do that, I need to expose this scale parameter. We can do that with Quick Search. So I'm going to click and drag on the scale connection, bring it out, and let go to bring up Quick Search. And now automatically you can see that we have expose scale as graph input and expose scale as a local variable. A graph input is an adjustable parameter that is visible from the outside, meaning the user can adjust this input when working with the node in the graph object editor. A local variable is similar to a parameter, but it's not visible from the outside, which means you can perform some logic within the atom and then assign the result of that to a local variable for later use within the atom graph. In this case, I want to expose it as a graph input because I do want the user to be able to affect this parameter from the outside. So I'm going to double click on that, and you can see it now has its own little node icon, and it is a graph input. You'll also notice that in our input section of the graph object editor, we have scale here. Now I want to make some adjustments to this parameter. So what I'm going to do is I'm going to click on it, and then I'm going to go to the graph variable editor, or Shift 2. Now you can see that we can change all of the important aspects of this graph input. For instance, the name, the type, and also what kind of control you can use to change it. I'd like to change the type of control from spin box to slider. This will make the user experience a lot better when changing this value. You can also see that I have minimums and maximums here. I'm going to change the minimums to 1 for the x and y. And then for the maximums, I'm going to make it 32. I'm also going to click this lock icon. This means that no matter what we do when we change the x or y values, they're going to remain locked together and be the same. So if I save my atom graph and then switch to my element graph, I'm going to click on my noise-based hue, and you can see we have that scale parameter. If I right-click and view this in the image viewer, I can now increase the scale, and you can see that our change is being reflected, and that the x and y are locked, just like we set. Our atom also retains all of the normal functionality that you would get from all the nodes in InstaMAT. So what I could do is I could override this slider range, and maybe instead of a maximum of 32, I could say 60. So with these values unlocked, I can just increase this to something above 32 if I wanted to. I could change the x and y and get whatever pattern I'd like. You can also revert to the defaults by clicking this curved arrow. And that's really great, but let's take it even further and give the user the ability to change the type of noise being used here by selecting 2 different noise options, as well as giving them the option to alter the noise's properties. Switching back to our atom graph, I'm going to bring in a cellular noise 2D. So I'll right-click to use quick search, start typing in cellular. There it is, cellular noise 2D. And I'm going to change the mode of the cellular noise from whirly to metaballs. Now I'd like to take the result of our cellular noise 2D and plug it into the hue input of our HSL color adjustment, but you can see that our pins are different colors here. We need to supply the right form of information here, and to do that, we can use quick search again. So I'm going to branch off a connection from the result of our cellular noise 2D, let go, and this time I'm going to type in .x. This is going to get the x value of the vector 2 that we're getting our information from. Now I can plug in that x value into the hue just like I wanted, and our types are matching. But nothing's really changed here. And that's because we need to do the same thing that we did for our Perlin noise 2D. We need to supply some information for the position and the scale. So again, I'm going to use that get texel coordinate that we had and connect that coordinate to the position of our cellular noise 2D. I'm also going to connect the scale to the scale input of our cellular noise 2D. Now, again, if I want to preview what's going on, I can right-click on the output and choose View Image Output here. We can see we're getting something different. I'm going to go back to my cellular noise 2D, and I'm going to change the disorder here. You'll see as I increase it, we're going to get some change in our noise. So perhaps what I'll do is put a value of 1 here. That's looking really cool. And perhaps I'd like the user to be able to change this disorder property from the outside. So like before, what we can do is I can click and drag a connection from this disorder and expose this disorder as a graph input. Now if I save and switch back to the element, I can click on my noise-based hue, view the output, and I have this disorder property here. But you can see we have it as a spin box. And the spin box is okay, but I think we can do better for the user experience, just like we did with the scale parameters, and we can change this to a slider. So if I go back into my noise-based hue atom graph, and I click on the disorder graph input here, I can go back to my graph variable editor and change it to a slider. So I'm going to save this again, go back to my element, click on my noise-based hue, and now we have that really nice slider here. But now let's create a parameter that gives us the option to switch between our Perlin noise and our metaballs cellular noise. To do that, we need to create an enum select node. So let's go back into our noise-based hue atom graph, and I need to find the parameter that I'd like to change. I'm going to want to give the user the ability to choose between the Perlin noise 2D and the cellular noise 2D, and they're both going to go into the hue input of my HSL color adjustment node. So this means I need to branch a connection off of the hue and type in the word enum into quick search. This gives us the enum select float node. Now, if I click on this new node, you can see we have some cases here in the enum switch compartment. In this cases area, we can define what options the user can choose from. So I'm going to change the cases to Perlin noise, Then I'm going to add a return, and on a new line, I'm going to type in metaballs. After clicking out of that, you can see that in our enum select float, we have Perlin noise and metaballs connections. So let's connect up our noises. I'm going to connect the result of the Perlin noise and connect it to Perlin noise. And then I'm also going to connect the X component of our getVector2 connected to the cellular noise 2D. Now there's one more thing left to do, and that is that we have to expose this case pin. So I'm going to click and drag again to bring up quick search. And instead of just exposing this as case, I'm going to type in noise type. And we can expose this graph input with the name noise type automatically. So I'll double click as graph input. We have that there. And so if I save this graph and go back into our element, we can now see that we have the noise type as an option here with a drop down. And I can switch between Perlin noise and metaballs. But I think I can improve this a little bit more. Instead of having disorder appear before noise type, I like to switch these two around. So I can go back into my Atom graph and I can look at my inputs in the graph object editor, and all I need to do is drag and drop noise type above, and you can see it switches it. But as I go back to my element and I check this out, if I go back to Perlin noise, you can see we still have this disorder parameter visible, and it's not doing anything for the node, which might be confusing for the user. So what I'd like to do is hide this disorder parameter whenever we have the Perlin noise type selected. InstaMAT gives us the ability to hide and show parameters based on whether or not some sort of defined condition is true. This is called vis-ex, or visibility expressions. And this means we have to choose which condition must be active for the parameter to be visible. In other words, we're going to define an expression that must be true in order to determine if the parameter should be visible. So I'm going to go back into my Atom graph, and I'm going to click on the disorder graph input, and then I'm going to go back into the graph variable editor. You can see this section here for visibility expression. So what I'm thinking is, if noise type is metaballs, then the disorder parameter has to be visible. Now, enums are organized starting with 0 and then 1. So in this case, Perlin noise is 0 and metaballs is 1. So if I go back and click on my disorder, go back to the graph variable editor, what I can say is noise type is equal to 1. Notice that I'm using two equals signs here because a single equals is an assignment operator, where two equals signs checks if the information before them is the same as the information after them. So because we're checking to see if noise type is equal to 1, which we know 1 is the case of metaballs, then we should have our disorder parameter visible. So I'm going to save my graph, go back to the element, and then check out our noise-based hue. We can see that our Perlin noise is selected, and therefore the disorder parameter is gone. However, if I choose metaballs, the disorder parameter has now appeared. I can adjust it. Maybe I want to go back. Now I want Perlin noise. And overall, this provides a better user experience for anyone trying to understand the functionality of this node. I can now go back and try and connect my text into the image input, change this over to metaballs, maybe change the scale. I can also change the random seed just like we did before. And all of our parameters and functionality are working. This concludes our tutorial of how to build a noise-based hue adjustment atom. Because we've built this as a single atom, you get lots of performance benefits. An atom is a single programming running on your GPU, so it will scale efficiently when you increase the resolution of your graph. Along with performance benefits, atoms also take advantage of all the features you'd expect from a node in InstaMAT, such as a local seed and support to switch from color to grayscale information. Now, there's a lot more to cover, so stay tuned for more Atom videos in the near future. Thanks for watching, and we'll see you in the next video. If you enjoyed this video, drop us a comment below, and don't forget to subscribe. For the latest news about InstaMAT, please visit our website and follow us on Twitter. You can find all the links in the video description below. Thanks for tuning in, and we'll see you in the next one.